Continuing our discussion on expectation and expected value, let's talk about the mathematical definition of a fair game. A game involving winnings is said to be fair if the expectation is 0. If on average nobody wins, or people lose as much as they are winning. This is what it means for a game to really be considered fair. Let's see how this would play out in a game. A person pays $2 to play a certain game by rolling a single die once. If a 1 or 2 comes up, the person wins nothing. If, however, the player rolls a 3, 4, 5, or 6, he or she wins the difference between the number rolled and $2. Is this game fair? We need to do a little bit of work before we get to our table. So let's write some stuff down. We're rolling a single die. So what are the outcomes on a die? 1, 2, 3, 4, 5, and 6. Okay. A person pays $2 to play. That's important because that tells us we're losing $2 if we play this game. Not all the time, but we have to pay $2 to play it. So we automatically lose $2. It's going to depend on the outcome of the die, whether we win anything. Let's take this a piece at a time. We have our outcomes. Now let's talk about our winnings. How much are we going to win? And I'm going to look in this in 2 different stages. How much did we win? And then minus our $2 to pay. So I'm going to do 3 rows here that really 2 of them don't play into our actual probability distribution just yet, but I'm hoping that it'll help you interpret what's going on in the problem and understand that a little bit better. So let's talk about winnings. If a 1 or a 2 comes up, the player wins nothing. So they win nothing. If, however, a player rolls a 3, 4, 5, or 6, he or she wins the difference between the number rolled and $2. So 3 minus $2 would be 1, they win $1. 4 minus 2 would be 2. 5 minus 2 would be 3. And 6 minus 2 would be 4. Okay, now we're going to look at, take into consideration how much it took to pay to play. They paid $2, so they've lost $2 for each one of these. They're always paying $2 to play, so for every single one of these outcomes, they've lost $2. Now let's write their net winnings. This row on net winnings is actually our random variable x. So we'll replace net winnings with a big old X, and we can also write in P of x here. And let's talk about the probability. So the winnings we get, we took the die outcomes, we subtracted off the $2, followed the structure of the game, subtracted off the $2. So what's the probability that we land on any of the numbers for the die? Just like what it was in chapter 4, 1/6 every time, assuming the die is fair. So all of these are going to have a probability of 1/6. Let's put this one in Excel. Okay, now when we find the expectation, x times P of x, and then we can add them up. One thing I want to point out, 0 is automatically 0. Notice how I have a positive 1/6 and a negative 1/6? They cancel each other out. The positive 1/3, negative 1/3, they cancel each other out. And I'm left with just a negative 0.3, a negative 1/3. That's how my sum is negative 1/3. Just pointing that part out. If you want to just add it all up and not worry about it, it's totally fine. Our expectation for this is negative 33 cents. So our expectation is negative $0.33 or 33 cents, which means on average we're losing 33 cents each game. Since this is not equal to 0, the game is not fair. Let's take a look at another example. A person plays a similar game to the previous one, rolling one die. If they roll a 1, 2, 3, or 4, they win nothing. they lose their fee to play. If they roll a 5 or 6, they win $12. How much should a person pay for the game to be fair? So this is a little bit different. This time we don't know how much they paid. So let's try to do similarly to what we did before. We have outcomes on the die. 1, 2, 3, 4, 5, 6. We have winnings, gross winnings. So they don't win anything, 1, 2, 3, or 4. For 5 and for 6, they win 12. Now, how much should they pay for the game to be fair? Since we're being asked how much should they pay, let's let some letter, I'm going to let this be B instead of X, because X has a meaning in a lot of these problems. X is our random variable. So let's just pick another letter. Let's let B be the fee to pay, their buy-in. Okay, so B is their fee to pay. On the last problem, we subtracted that buy-in from all the winnings. So we would do the same thing here. Subtract B from all of them. Now this time, the winnings are not tied to the roll on the die, other than to say, for these numbers you get nothing, for these other numbers you get something. So we can actually group them together. We can group the 4 zeros together, and we can group the 2 12s together. It'll make our calculations a little bit simpler, and our table a little simpler to read as well. So now for our table, X is going to be the net winnings. So we have in our green group negative B, and I'll do this in green so we can see where it comes from. And then in our orange group, we'll have 12 minus B. Now for probabilities, I'm rolling a die. 4 of the outcomes give me negative B, so that means my probability will be 4 out of 6. 4 outcomes out of 6 total. And for the other 2, 2 out of 6. Okay, now we need to find our expectation, and we want the game to be fair. So we want to put a condition on our expectation that it is equal to 0. So let's do the sum of x times b of x. We'll have negative b times 4 6 plus 12 minus b, got to put it in parentheses, times 2 6. This equation has to equal 0. We need to do a little bit of algebra. I'm going to move over so we have some more space. Negative b times 4 6 plus 12 minus b times 2 6 equals 0. I need to solve for this variable b in my equation. Good news, this is a linear equation. It's just got fractions in it. Since it's an equation, I get to multiply by whatever I want to. Let's multiply by 6 and get rid of those fractions. So we're going to multiply the whole left side by 6 and the whole right side by 6 to clear the fractions, to cancel with the denominators. So we'll distribute this 6 to both of our terms. Terms are separated by addition or subtraction, in case you forgot. So negative b times 4 6 times 6 plus 12 minus b times 2 6 times 6 equals 0 times 6 is just 0. These multiplying by 6's, these are 6 over 1's. And we can cancel, and we're leaving behind 1's. When we multiply by 1 or we divide by 1, we keep the same number. So in this first term, I really have negative 4b. In the second term, I have 2 times 12 minus b. And that has to equal 0. We can distribute the 2. 2 times 12 is 24 minus 2b. And we have like terms with the negative 4b and the negative 2b. 4 and 2 will give me 6, so negative 6b plus 24 equals 0. And I've got to solve for b, so I can add 6b to both sides. You could subtract 24 from both sides, it doesn't matter. 24 equals 6b, divide both sides by 6, b equals 4. So someone should pay $4 to play for a fair game. Gambling is not the only place where expectation is important. In the next lesson, we'll talk about insurance. Insurance is really just a big discrete probability distribution problem.